So we can start from here. What you've seen in the slide, there is a helical screen. In the helical screen, load is applied through the center of the spring. Say if you put a some flat thing over here and put some force, either you sit down, the load always go through the center of the spring. Then at the bottom, if you have spring support, the reaction force will also work through the center of the spring. So if helical spring is failed due to the shear failure of the wire. Shear failure means the wire become two parts. It might become anywhere, or might be here, or might be here. Anywhere, if one wire become two parts, then it will not able to absorb the energy. That means it's complete failure. But in leaf spring, if one plate break down or fail, you can change that plate only. Okay, this is the advantage of leaf spring. While helical spring, this is the problem. Disadvantage that it is failed, you need to change the whole spring. Now, what is our purpose? You like to design a spring or you like to buy a spring, you need to make sure it meets your purpose. That means when you apply the load, it will not fail or break down due to the application of load. So normally I told you that is fail in the coil become two part. So when a parts become two part, that means shear force is working there, or shear force means shear stress. You divide by the area, you will get the stress. So we need to figure out a equation that if you apply a load in the helical spring, how much stress developed there. So that stress is shear stress divided by tau. And helical spring, they have some parameter. Number one thing, the diameter of the wire, that is called small d. Then mean diameter of the spring, like from here to here, that is big D. Then you have length of the spring. Then you have material property, shear modulus G of the spring. Then you have one more parameter, free length of the spring. If free length, say L0, after applying load, compressive load, length coming right over here, LF. In that case, how much change of length of the spring? Delta L equal to delta naught free length, load free length, divided by LF. So if you have that delta L due to the force F, then you can figure out the spring constant. Spring constant will be F by delta L. Okay. Now, our purpose is to how spring fail, how much shear stress work there if you apply load F. That we need to have a derived formula. So if I cut right over here this spring, this wire, then we'll make the free body. So if I like to draw by hand sketching this spring, say right over here, it is failed. So I cut it right over here and I took the bottom part. I like to make the free body. This is F. So right over here in the wire, kind of diameter like that, right? This wire gradually go upward direction. So right over here, this wire same amount of force F. Now you look carefully, this is not balanced because this F is working directly downward, right? And this F working upward. What does it mean? So there will be a moment, right? So if I can't write over here this thing that I am showing in the left side, that vertical force is working downward, F1, downward force. So in the wire, there will be upward force. F. Now you see, direction of F is working along this direction, right over here. That means he is pushing down, he is pushing up. So these two try to rotate the spring in clockwise direction. Now, who will protect it? Normally, if you look at the spring, it do like that, vibration, or it compress or elongate it, axial, but it never do tilt motion. There is a specific reason why. Because these two, this force and this force will make a couple and bending along clockwise direction. And you never see there is no, so what will be the bending moment, this M? This bending moment M will be F into distance between two forces. So what is the distance from here to here? Mean diameter from here to here is D. And from here to here is D by 2. So M equal to F by D by 2. But if there is a bending moment, what bending moment does? It try to rotate, try to bend the parts, right? Like in the beam. If you have bending moment, what around the beam, that's why it bend like that if there is a downward load. So you never see a spring under load, it deflect, bend like that. A wire bending like that. Okay. Or you might never see that is bending downward like this one, bending like that. No. Because it don't bend like that, but suddenly the spring wire become two part. That means this work like a torque, because it become two part is possible by only if direct shear force work, Fs. So direct shear stress, tau s equal to Fs divided by area. This is on. Now other, and since this is not balanced, right? Only without torque it will not be balanced. But it becomes two part. That means direct shear and also there is some other shear work. What is torsional shear force? That's why instead of M, we are thinking right over here working torque. And these two, this F and this F, try to rotate the spring in clockwise direction. That's why that will be protected by this wire resistive, and this will be in anti-clockwise direction. And instead of M, we will say this is torque. Why? Torque also creates shear stress, right? Tau equal to TR divided by J. So a spring becomes two part, mainly two reasons. One is direct shear force, other one torsional shear force. So from that concept, we make the theory right over here. And we'd like to figure out the stress at this phase. So this phase, you see force F working parallel. That means this force will create direct shear force. Tau is equal to Fs, direct shear force, divided by area. Or we can say tau is equal to Fs. What is Fs? This F divided by area. What is the area? Pi by 4 diameter of the small wire. This is direct shear. Now, the other shear is torsional shear. This torsional shear, tau equal to TR divided by J. This TR, T will be this one, MD by 2. And this R will be radius of this wire. That means small d divided by 2. Go up here. Okay. So this is torsional shear force and this is direct shear force. If you add these two, then you get magnitude of the shear force in the spring under load F. Okay. So let's see how we can derive this one. If I go new shear, one second. Okay, look, that one. So right over here, two forces. One is F, other one is torque. So both will create, obviously F working parallel to the cross section, and torque also creates torsional shear force, shear stress. So that means this wire right over here, the shear stress will be same all around the body, right? What is the shear force F is working? This is the ring surface parallel right over here. That means this is shear force. So in that case, shear stress will be F divided by area. So that is this one, F by area, direct shear. Now, due to the torque is md by 2. What is the formula? Tau equal to TR by J. So that we put over here. So maximum shear in the spring will be summation of direct shear stress plus torsional shear stress. Now, you need to figure out the value of T, torque. So value of torque is Fd by 2. If you take moment over here, you get the torque. So torque equal to Fd by 2. And right over here, you need the area equal to pi by 4 d square. That means this small area. J, the polar moment inertia of the spring wire, R equal to d by 2. Now all this value, you just put it over here. Okay. So value of torque Fd by 2. This is our torque. This is the maximum torque will develop in the not torque, sorry, maximum shear stress will develop in the spring. Number one, shear force due to the direct shear stress due to direct shear force. Other one, shear stress due to the torsional shear stress. So T equal to Fd by 2 or R, diameter of the rod is d by 2. And the bottom we have J equal to this one. So this is J. Top TR, this portion. Then F by A. This is F. What is the area of the wire? Pi by 4 d square. D mean this area. The pi by 4 d square. That means this area. So if you simplify this equation, you just simplify, take common this one part. You take common this part over here 1 plus small d by 2d, this one. And if you multiply again these two terms by this value, you will get ultimately this one. Okay. Now, right over here, you just simplify. You put a spring index. This index means mean diameter of the spring divided by the small wire, diameter of wire of the spring. So you will get d by d. So this is the value of C. This is a constant. Diameter of the mean diameter of the spring divided by the wire diameter. The value is more than 1. So right over here, you put d by small d by big D, you put 1 by C. Right over here is 2. So after you rearrange 8 FD pi by pi d cube plus this value here. 2C plus 1 divided by C. And what is the C? This value, d by d. So your formula, because if we think this is a constant Ks, then tau is equal to Ks into 8 by pi d cube. Now, did we making any mistake? Who can tell me? Let's see, we have 21. I'll ask who? Mirhab, roll 130. You are here? Mirhab? You're not here. I'm taking the attendance, actually. Okay. Section A. Okay. Rimi, Nasrin Rimi, roll 131.
Yes, sir.
Yeah. Okay. Tell me, did we make any mistake?
So where?
When we derive this formula, coming over here, right? We are missing anything or not? The spring, did you see the spring, right?
I can see.
Okay, so spring wire, is it straight or curved? After you make the spring, is straight?
I didn't understand your question.
I'm saying, say I'm giving a wire, okay?
Yes, sir.
So wire has a diameter, right, and length. Say I'm giving you 4 feet wire, so obviously it has a diameter, right?
Yes, sir.
Okay, I'm telling you, make the spring with this wire. Then what will the shape of your, right now it's straight line, right?
Yes, sir.
But after you make a spring with this rod, then shape will be still straight or curved?
Curve, sir.
It will be curved, right?
Yes, sir.
And torsional shear stress we derived before, right?
Yes, sir.
That we apply on a straight bar or a round bar or a curved bar. Torsional shear stress formula, how did we derive?
Sir, straight bar.
We derive in a straight bar. You see. Okay, what is your ID?
131.
131. Okay. Right over here. That we derive the shear stress in a circular shaft or rod subject to torque. But what is the condition? The cross section has to be circular. Other conditions, it has to be straight. But in the spring, what happened? Initially, this rod was straight. Then you carve it by special machine, make the spring. But we are applying torque like this, this wire, right?
Yes, sir.
But this wire, at least this portion, all of the portion is not the straight, it is curved. But we are applying right over here, but applying personal formula in a curved bars. This is TR by J, this is shear stress formula for a round and straight bar, right? On cross section, but length is straight. But we are applying in a curved bar, it's right over here, curved rod, right? So we are not accurate. That means right over here, tau equal to Ks 8 FD by pi cube. This result is not the accurate. Why not accurate? Because we apply torsional formula in the curved bar instead of straight bar. So we need to have a correction factor. Okay. You see right over here, I'm saying, assume that spring wire is straight. It also subject to torsion and direct shear. But actually, spring wire is curved. The curvature in the spring rod increases the shear stress. So this is counted by another correction factor, Kc. So whatever the result we found, our result was this one, tau equal to Ks into this value. What is the value of Ks? Ks equal to this one, or also given over here. But we cannot use this formula because this is used for straight bar, but our bar is round. So if this equation you multiply a or more correction factor. So it's saying curvature in the spring rod increases the shear stress. So this is accounted by another correction factor Kc, which is known as curvature correction factor. So this formula you got from the derivation multiplied by the Kc. So this is our formula. Now there is a two constant Ks and Kc. We can combine these two with single constant. We can say Kb. Kb equal to Ks into Kc equal to 4C plus D 4C minus 3. So after these two constant, we can make or express by a single constant that is called Kb. What is the value of Kb? Kb equal to Ks into Kc. That equal to 4 into C plus 2 and 4C minus 3. So this is the formula of our shear stress in a helical spring. What is the Kb?
Sir.
Right over here. Yes.
স্যার এখানে অ্যাক্টিভ কয়েল কাউন্ট করা হবে না স্প্রিং এর ক্ষেত্রে?
Active coil number.
Yes.
Yeah, we'll do. We'll not in the shear stress, because in the shear stress, it don't mean that your coil will break down. It can break down anywhere, right over here, bottom, or we have quitted the half, right? It might have bottom too. Or it might be failed right over here. Okay, that's why shear stress will be uniform, will be by same amount. Say after calculation, if this value you got 400 psi. That 400 psi will be for all of the wire in any location. You will experience this much stress. Okay. Now, if you like to figure out the deflection of the spring, say you have a spring, say you apply the force F. So obviously it will react through upward by same and equal amount. Okay. And this spring, after you apply load F, then it squeeze little bit. That means this mass portion equals. Right? So that is called deflection of the spring or deformation of the spring. Say deformation is Y. So also we need to know the value of Y. So value of Y or deflection equal to 8F dq by this value. And right over here, you see, if this number of turn, if you increase, your deflection will be increase. Okay, you are pulling. Say you have a spring only 2 turn, same spring, but you have 6 turn. Then your Y value, deflection of the spring, right? In that case, say you apply compressive load for this spring, you might make it right over here. Actually, it can break anywhere. It can break right over here. It can break right over here. But deflection, how much it is deformed, it depends on number of turn, number of n. That's why number of turn they express with big capital letter N. So if you have value of Y deflection, then what is the value of the K? Spring constant. Spring constant K equal to F by Y. What is F? F is the applied force on the spring. So F by Y, or you can say F by delta. Same thing. Some book write down Y, some book write down delta. So I put both on Y delta equal to Y equal to this value. And this one we are not deriving it over here, but we will show you that how it is coming. So if you have the deflection of the spring or deformation, you can get spring constant, because spring constant K equal to force per unit deformation. So if you need 10 Newton of force for 1 millimeter deflection, that means your spring constant will be 10, you see, Newton force. That means 10 Newton, I can say 10 Newton per millimeter. That will be the spring constant K. So what I'm saying, if you know the applied force, and if you know the amount of deflection by the spring, how much it is deflected, then you can figure out the spring constant K. For example, still it is in the market. If you weight measure, say there is a spring, holding the spring, and this one you can hold with your hand, and in that spring you weight your something. You say 5 kg rice bag or 2 kg rice bag. You go to the market, you buy 5 kg beef from the market, Now you're saying this, the measurement might be not right. So you can say this small scale is available. And how it is work? They have a spring, and after you hang your bag with this scale, spring will go bigger. Say, for example, by 2 inches. And if you know the spring constant, you can easily figure out the amount of weight. Because spring constant for this one, say, has a spring constant 5, for example, I'm putting in kg, 5 kg per millimeter. So after you hanging the weight, you see the spring is go bigger by 4 millimeter. So what was the weight? 4 into 5, because this is spring constant. For 1 millimeter deflection, go bigger or decrease, you need 5 kg weight. So for 4 millimeter, you need 20 kg weight. 4k into y deformation. Okay. So right over here, you need to know what is the n. N is the number of turn in the spring. How many turn you have? G is the shear modulus or modulus of rigidity. G. And K is the spring constant. Now, you might have questioned that how we got these two formula, right? These two formula we use, figure out by some, applying some energy equation, strain energy equation. Normally, we don't derive this one, okay, in the undergraduate level. But I can show you the slide that how it is actually working over here. Let's see. Right out here. You see, to figure out the amount of deflection and spring constant, they use Castigliano formula. Okay, and they use the strain energy method. 1 second, please. Hello. Walaikum salam. Yeah. No, তুমি লিংকে আপলোড করো ক্লাস। আচ্ছা ঠিক আছে, তুমি ওকে, তুমি ইমেল করে দাও। না, ক্লাসরুমে না, তুমি ইমেল করো, ঠিক আছে? ইয়া, ওকে। Hello. You can hear me?
Yes, sir. Yes,
Okay.
sir.
Yes. So to figure out the deflection and spring constant, they use Castigliano method. So what they did is a U. What is the U actually? U is the strain energy. You know, in the spring, we know two forces work. Only one is shear force, other one is torque. Okay. So you see, this is the L. L mean what is the total length of wire in the spring? How to figure out? You figure out the 1 ton. What is the length of 1 ton? Length will be 2 pi r, or you can say pi t. And you have 10 length ton multiplied by 10. So it is the n number of ton multiplied by n. So this will be length L of the wire. And this is, you see, this is a torque value, you know. This is L, and this is G, shear modulus, because it failed by shear. So you need to use the shear modulus over here. And this F is the shear force on the cross section of the wire. So what he figured out that a spring, how much energy it can absorb total. energy. So that amount is this one. This one. Then he put change the value of T, L, all value and area, polar moment of inertia. Then you got this equation. Now, we figure out the value of deformation. If you differentiate this one with respect to F, you get Y. What is the energy? Joule, right? Joule. U is the joule, remain at the top. J divided by, in the bottom what you have? Force, Newton. And left side, Y. Deformation, say M. So what are you getting? Joule equal to Newton meter. Unit is same. That's what they did. They are saying deformation equal to change of total energy divided by amount of force, change of force. We have deformation Y. So they did del U by del F, differentiate this one. Then finally they got Y equal to this value. So you already got Y value. That means deflection of the spring. So you are getting Y equal to 8 F, then big D Q, then M divided by D to the power 4 into G. Now what is the K? K equal to F by delta. That means, or F by Y. So from here, you can figure out F by Y. F by Y equal to how much we figure out. So this F by Y equal to K. Then we figure out K equal to D to the power 4 G 8 DQ N. Okay. So we have three formula. Value of K, value of deflection, other one value of amount of shear stress in the spring, like this one. Okay. So right over here, I just put all the formula. Okay. Now we can solve the problem 1. In problem 1, it's a determine the maximum shear stress. That means shear stress means we need to figure out the value of tau. And elongation in how much its length is this. That means we need to figure out the delta or Y. Elongation in a bronze helical spring, it's a bronze, so you can figure out the G. Even if G value is given over here, but if you know the name of the material, then easily you can figure out G by from handbook or from textbook or also from the website. So value of the G is given in the problem. Helical spring of 20 ton, so it has 20 ton, that means N. 1 inch diameter wire, so small d value is given. On a mean radius of 4 inches, that means this is capital D. When spring is supported by a load of 500, that means F value is given, G is given. So you need to figure out the amount of tau, you need to figure out the amount of delta. And easily you can figure out, because tau equal to F 8F D to the power. If you look previously, tau equal to 8FD divided by 5DQ, then KB. So 8FD divided by pi dq, right? Into we have kb. So you see tau equal to kb fd pi dq. So this see everything is over here. And what is kb? kb equal to 4c plus 2, 4c minus 3. What is the c? d by d. I see c, value of c equal to bigger d. That means 4 inch divided by small d, 1 inch diameter. This is d by small d is the value of c. So if you figure out the value of kb, then just put over all the value. It's easily you can solve it. Okay. So we are not solving that one. Right, kb value right over here. Okay. Now let's solve problem 2. Problem 2 is saying compute or calculate the maximum shear stress developed. That means tau, right? Maximum shear stress developed in a phosphorus bronze spring having mean diameter 200 millimeter. That means they give a mean diameter like this one. I'm sorry, mean diameter D, consisting 24 ton, number of N given. 20 millimeter diameter wire. That means this is small d. When spring is stressed 100 millimeter, that means y or delta value given equal to 100 millimeter. G value is given. So you need to figure out maximum shear stress in the spring. So what is the shear stress formula? Tau equal to kb, then 8 f d divided by pi d to the power q. So you see big D given 200 millimeter, big D, and tan given n equal to 24. But over here you don't need to calculate the tan. Small d is given 20 millimeter, right? But we need value of kb. So kb equal to 4c plus 2 divided by 4c minus 3, I think. And what is the c? C equal to small d, I'm sorry, bigger d by small d. So bigger d 200 millimeter, small d 20 millimeter. So you can figure out the kb. But force is not given. So at first we need to figure out the force. Then you put all the data over here, you can figure out the tau. So let's see how we can solve it. Then I'll give you a break. Right over here, this one. Okay. It's saying mean diameter of the spring 200 millimeters. So D equal to 200 millimeter. Then you convert in meter. Number of turn, they say I put small n. If you want, you can put capital N. 24. Diameter of the wire 20 millimeter, right over here. So D equal to 0.02 meter. Delta spring, you say the when spring is stressed to 100 millimeter, that means you compress it, stress means turn. You will elongate it by 100 millimeter. Okay. So this is delta, or you can say value of y. G value 42 gigapascal. You convert in Pascal, Newton meter square. or need to figure out? Spring constant K and maximum shear stress. That we need to figure out. What is the spring constant? F by delta. F is given. It's a 100 millimeter stress to 100 millimeter. So that's the delta. But F is not given. If you know the F, then you can solve everything. You see, this is shear stress formula. D value we know. Small d we know. KB we know. But F we don't know. And they want K. K equal to F by delta. This is the equation for the delta. And you see, equation of delta, delta is given. So from here you can figure out the F. So it's a deformation of the spring, delta equal to F dq into N divided by small z to the power 4 into Z. This is the formula. From this formula, if you rearrange, you can figure out F by delta. And F by delta is the value of K. So this is our K value. In K value, is small d value, we already have it. Z value is given. Big capital D value is given. Number of turn is given. So from here, we got K this one, or 4.44 Newton per millimeter. That means if you like to deflect the spring by 1 millimeter, you need to apply 4.4 Newton load or force. So how much spring was compressed? 100 millimeters. So for 100 millimeter, how much force you needed? You can easily figure out. Okay. So is K equal to F equal to K into delta, because we know delta equal to not delta, spring constant K. K equal to F divided by delta. That means if you see in terms of unit, N is the Newton unit of force, delta is the, say, millimeter or meter. So we got value of K this much. Now, how much the deformation? 100 millimeter. Delta value is given 100. So F equal to K into delta. Delta, so you get value of F. This value of F, value of F, you put right over here, you will get the shear stress. You put right over here, everything you put, you get value of K value, we already got it, right? So you just put over here, you will get the shear stress. That would be it. You see, we got the F, then we put over here. We got the tau. Tau equal to 31.62 megapascal. Okay. So any questions from anyone? Any question about the spring?
Sir, what is the value of Kc, sir? What we have gained from Kb?
What is the value of C?
Kc, sir, Kc.
Kc, let's see. Okay. Not over here, you're talking about the Kc. Kc value, actually, we take it out with one constant. At first, we got the, we look at the derivation, we got one constant. This is Ks. Okay, this is Ks. But this is not accurate because we apply torsional formula in a curved bar. So that's why we multiply by another correction factor that is called Kc. So right over here is coming Ks into Kc. Now, this Kc, we call it Kb. This is figured out experimentally. There is no separate value for KC. You can figure out how. At first, you figure out the value of KS, right? KS is this one. Okay. Then you figure out KB. So KB equal to KS into KC. So KS you already know, then figure out the KC. But right over here, we don't need it because in our formula, these two by combine these two represent by constant KB. And directly figure out from here KB equal to this one. Okay. What is your ID?
Sir, 111.
111. Okay, good. Anyone? No, right? Okay. So I am giving you 5-minute break. Okay. Come. Let's see. I can share with you 1 second. Did you see? Hello.
Yes, sir.
Okay. So name of this chapter is combined stress. Okay. So combined stress, by the name of this chapter, you might realize something, right? That means you need to combine two types of stress, then figure out the resultant stress. For example, in beam, what do we have in beam? Say this is a simple beam and it is supported, say left hand on a roller and right hand is the support. Okay, and it's subject to load. Now tell me, how many stress in the beam? Anyone? How many stress in the beam? Asif, roll on 21. You can tell me how many stress in the beam. Asif, you are there? Asif, not there. Rivan, roll 109. Rivan, he is not there.
Yes, sir. Assalamu alaikum.
Who is Rivan?
Yes, sir.
Okay. Do you know what is beam, right?
Yes, sir.
And in the beam, how many stress is in the beam?
Sorry, sir.
How many stress in the beam? Okay, could you hold on 1 second? 1 second, please. Sorry. So, yeah, tell me how many stress in the beam?
Sir.
Hello?
Yes, sir. I can hear you.
Rivan,
Yes, sir.
you
Sir,
can tell me that,
sir, two.
give me the name.
Sir, I don't remember right now, sir.
Number one thing, bending stress, sigma.
Yes, sir.
Sigma equal to MC or My by I. Other one is shear stress. Tau equal to BQ divided by I. So shear stress, normal stress or bending stress in the beam, it works along longitudinal axis of the beam direction. You know, stress is a vector. You need to have a direction of the stress. So you see, and there is a shear stress in the beam. What shear stress does? shear stress try to divide the beam into part. And what is the bending stress? Bending stress, it try to bend the beam, right? For example, if you have a straight beam and you have bending moment you apply right over here and right over here, then what will happen? Bending moment M you apply. This beam will bend like that, right? It will bend like that. If it is bent, then what will be over here? Compression or tension? Anyone? Right over here, it will be
Compression.
compression. And right over here, tension, right?
Yes.
Now, how compression and tension actually coming? If I explain you in other way, that you have a beam, now there is a bending moment M. This bending moment M, I can replace by two force, because see this M, right? So I can think that this is one force working left direction, other force working right direction, M. Say the depth of this beam is D. So this is also F, and this is D. So I can say that M equal to F into D. So what is the F then? F equal to M by D. So this, what is the rotation they are making? This one and this one. They are making rotation anti-clockwise, right? So this bending moment also anti-clockwise. So in the right side, I can replace this bending moment by two force. One force working along this direction, other force working along this direction. Two force. Same way, this force, this bending moment, I can replace by two force. Right over here, other thing going right over here. Now what you see? This bottom portion of the beam under tension and upper portion of the beam under compression. We try to squeeze and the bottom one try to pull, okay, tension. Now, so you see, then you have shear force or shear stress. They try to pull the beam along downward or upward, try to divide the beam into parts. So if I consider a point right over here, this point, you will have two types of force. One is tension, other one shear. Say tension is along this direction, shear force, and tension right over here. So this resultant of these two force, this is tau, this is say sigma t. So resultant will be along this direction. So this resultant, if you not count this resultant, then your design will be wrong. You need to count the resultant of two force. Okay. For example, you sitting or standing right over here. So your one friend pulling along this direction. Other friend pulling you along this direction. Which way you should go as per mathematics? You should go resultant along this direction, right? So without considering the resultant, your result will be wrong. Other example, say you have a rod or bar, circular bar attached with a wall. Now you are applying torque. So what can stress will be in the bar? Number one is tau, shear stress due to the torque. TR divided by J. And shear stress what will do? You try to make the this rod or bar, circular bar, into two parts, right? Now, there is one more force working along this direction, force is F. What is this force? Actually, tensile force. He's trying to make bigger, pull, right? So due to the F, what will be the stress, normal stress, because force working perpendicular to the surface. This sigma will be F by A. Now we see in this shaft or bar, there is two stress working. One is sigma, other one is tau. So what would be the resultant of these two? That you need to figure out by combined stress formula. For example, if you think this is this section, this shear torque or shear stress try to divide, and this F try to pull him along this direction, and shear stress try to divide over here. So what will be the resultant? The resultant will go along this direction. Okay, so we need to consider the resultant effect of the stress. For example, you are carrying oxygen gas in a cylinder, that means a pressure vessel in a truck, bigger truck, right? So what kind of stress in the wall now in the pressure vessel? Sigma T is the critical one, right? Sigma T equal to P into R divided by T. Now, due to the road condition, we have four wheel of the truck, right? Say one wheel over here. So due to the road condition, sometimes the vehicle or truck, say it might go like that incline. And if you watch some YouTube video, they'll see on 18-wheeler, it's a running through the highway at certain speed, and due to the wind, one wheel go up about 1 feet. What does it mean? He tried to twist the tank, right? If this wheel go upward direction, then this end will go up. That means he's trying to twist the tank. That means this, due to the twisting, there will be a torsional shear stress. So a tank cross section like that. So it is your kind of hollow shaft. So your shear stress will be tau. You can easily figure out TRYJ. So in this tank, if you design only considering sigma T, you are not thinking about that in the transportation, there might be road condition or might be the gusty wind, it might experience torque. Then your design will fail. Similarly, say a lot of ships carrying crude oil is circular shape tank, oil tank, right? So it is also a little bit pressurized. Then due to the wave, a ship is huge long, right? Say 400 feet or 500 feet long. So if wave hit this portion, then what will happen? It will immediately go tilt motion, right? Due to the tilt motion in the tank body, it will create torsional shear stress. So you see, everywhere there is some combined stress. So that we need to study whenever you design something. You need to make sure that if you have two stress, what is their combined effect? That you need to figure out. Okay. So I just giving you the introduction of this chapter. Now we need to learn some definitions. Say you need to buy computer. You need to know what is the RAM, what is the CPU, what is the gigabyte, or what is the megabyte, right? So similarly, there is a two term. Number one term, plane stress. Other term, plane strain. What is the plane stress? Plane stress means, say you have a plate, and this plate along this direction, x-axis, y-axis, horizontal plane, right? Vertical, z-axis. So if I pull in x-axis and y-axis, but I am not applying any force in z-axis, then we'll call it plane stress. So if I pull it along xy plane, what will happen about the thickness? Thickness will be reduced, right? So along z direction, there will be no stress, but there will be strain. Okay. So right over here, it's a what is the definition of plane stress? It's saying plane stress is defined to be a state of stress in which normal and shear stress are zero in the direction perpendicular to a plane. For example, in your table, you have a table, right? In the table, you see there is no load along x and y direction. Right now, only load in vertical direction. You might put your laptop, your desktop by your monitor, right? So this is force working only vertical direction. But in some situation, say this is my cell phone, if I pull this way, that means if I apply all the force in single plane, but in vertical direction there is no force, then we'll call it plane stress. But what happens if you pull a plate in horizontal plane? Obviously thickness will be decreased. If you compress, then thickness will be increased. So thickness increase or decrease means in z direction there is no stress, but there is strain. So that it's saying stress in z direction will be zero for xy plane, but strain in z direction is not zero. That is called plane stress. Other thing you need to know, plane strain. What is the plane strain? For example, this one is simple plate, right? So if I pull, what will happen? Along x-axis or y-axis, his length will be increased and the thickness will be decreased. Now, if I increase the thickness, say how was the cell phone this length or this width? Say this is 5 inches or 6 inches. This is say 4 inches or 3.5 inches, right? But thickness I am increasing to 20 inches. Then I'm pulling. Then what will be the deformation along z-axis? That deformation, theoretically, there will be some deformation, right? But compared to the length and this thickness, length and width and the thickness will decrease very little bit. That thickness or deformation we can ignore. For example, you are carrying natural gas from Kumilla to Dhaka through a long pipeline, and inside is pressurized, say 400 psi pressure. So what will be the stress in the pipe? Obviously, kind of pressure, right? So you have sigma T equal to PR divided by T. Then you got sigma L. Sigma L equal to PR by 2T. So you can figure out what will be the stress in the pipe. Now, what is the sigma L? Sigma L try to work along length of the pipe or pressure vessel. That means longitudinal stress. That means along longitudinal direction, there is some stress force working. So due to that force, obviously the length of the pipe will little bit increase. For example, you buy a balloon, you put air by your mouth, your radius will be increased due to tangential stress. Length will be increased due to the longitudinal stress. So similarly in the pipe, there will be some elongation. But compared to the length, that elongation is negligible. So plane strain, it's saying that it is defined as a state of strain in which strain in the direction normal to the plane assumed to be zero. So say this is my notebook or a plate. I am pulling along this direction, pulling along this direction. So if I pull it, then thickness will be decreased. If I press, thickness will be increased. But now we think this thickness of this my notebook is 10 inches or 20 inches. Then when I pull in, still it might be decreased little bit thickness, but compared to the other two dimensions, that is negligible. Because what is the strain? Your formula. Strain equal to delta L. Change of length divided by original length. So thickness by notebook making 20 inch, that will be original length divided by 20. And after I pulling in this direction, it might decrease a little bit, point say 0.0001. So in that case, a small number, even if divided again a bigger number, so it will look close to be 0. And that's why in the plane strain, it's saying it is defined to be a state of strain in which the strain in the direction normal to a plane is assumed to be 0. Normally, it happens if dimension of the structure in one direction, say for example Z direction, is large compared to the other two directions or XY direction. Strain in Z direction will be 0 for XY. That is called plane strain. Okay. So sometimes we put this question in the exam. What do you mean by plane stress and what do you mean by plane strain? Okay. Now, right over here, we have 10 more minutes, right? Hello?
Yes, sir.
Okay.
Yes, sir.
I like to keep you with parallel two sections, A and B. Okay. Say in the right over here, before that, I like to show you something. Say in your ceiling fan, hanging by rod, right? So at the top, there is a roof. So attached ceiling fan over here, then ceiling fan, suddenly it has a weight, right? So weight working downward. So what kind of load in the ceiling fan? In the rod. So obviously the reaction in the support at the roof will be upward. That means it will be F, right? So what kind of load in the rod? Anyone? This is called what type of load? Uniaxial tension load, right? Your rod of your ceiling fan is subject to tensile load. So what will be the stress? We can figure out. Anyone? What will be the stress? We can easily figure out if you know the area of the rod, right? So stress equal to F by A. How much shear stress in the rod? Anyone? Anyone? How much shear stress in the rod?
So 0.
0. Why 0? Because
It shear stress works
shear force was parallel to the
parallel to the applied
cross
force.
section, right?
Cross section. Yes.
Good. But in this object, there is no force working parallel to the cross section. What is your idea?
Sir, 116.
116. Okay, good. I think it's first time responsive. But we'll show you that there are some shear force work. Depends on how you are looking to that object. You see, if I cut right over here, then I can make free body of bottom one. So this is force working downward. So how to do force in the upward? Same force, right? Still, there is no shear force working in the in this structure or bar. But if I draw the shear force, I cut the object in different positions. For example, and I will wide to understand. Say, I am cutting right over here, like in the angle. Now I'll make the free body of that portion. So if I make the free body, say this is portion, and I'm just to figure out this, and this is the angle. Now in downward direction, I have a force F. So up will be force in upward. Then summation of force along y direction is 0, right? That means my body is balanced. Now I look right over here, that what's going on over here. Okay, so I am making two lines there. One line I'm making perpendicular this surface. This is an inclined surface, right? This is blue color. This is perpendicular surface, and along this direction is parallel to the surface. Now, if this angle is theta, if this one theta, then this angle also theta. Say this is theta. Then if this is theta, this F I can make into component. This component will be F cos theta. And this component will be F sin theta. Now look, what did you see? You see this F, though working vertically, but some component of F is working parallel to the surface. And this one working perpendicular to the surface. So this force is actually shear force. So if sine theta 0, if theta 0, then what is the section like that? In that case, there will be no shear force. But if this theta of certain value, then you see there is a shear force and also normal force working in this surface. So if you cut a surface, remember there work one normal force and there will work one shear force. Now, even we like, actually what happened? Why shear force work? Say, I give example that this is ceiling fan, but you are pulling with higher force, then what will happen? Gradually, the rod will go bigger, and at the middle, it becomes two part, tear off. That means, if you look at the test in the solid mechanics class, gradually you increase the force, there will be necking, and right over here, it will break down, become two part. That means it is shear, right? So that means even you are pulling, but at some point, material experiencing some shear force or shear stress. That's why it becomes splitting two parts. That I am showing over here. And this shear force, we got maximum when the angle is 45 degrees. Okay. So just right now, remember, if you cut a body, there will be a normal stress perpendicular to the surface, and there will be shear force parallel to this surface. Okay. Now, say your 10 friends got together and you went to Coxbazar or Sylhet, and you climb top of a hill. Okay, top of a hill, and you see there is a big stone there lying at the top of the hill, and all of you, some of friend is kicking the stone along this direction, and someone kicking from here, someone kicking from here, and someone pulling, and someone sitting at the top. But the stone is not moving. What is the reason? Anyone? Is not moving. That means the applied external force and the reaction force become zero. That means sum of Fx, sum of Fy, sum of Fz will be zero. So all those, I draw the blue color line, that is external force, and also it has a weight. Then it has a reaction. If it is supported at multiple points of the ground, the reaction force will work upward along the direction, right? So when summation of Fx is zero, similarly summation of Fy equal to zero, then this body will not move. Then Fy equal to zero, then summation of Fz equal to zero. Then it will not move. Now, it is not moving, and also it is not rolling. Rolling means tilt, কাঁদতে দাও. Why? Because moment, summation of moment along x-axis, that means mx equal to zero. Summation of my, that's knowledge from your engineering mechanics, my equal to zero. Similarly, summation of moment along z-axis equal to zero. Then this body will not tilt. Okay. Now, why it is not breaking? Other question. It is not breaking because your applied force or load is low than the resistance of the material. Material has higher resistance. It might be break if you put more load. When the resistance of the material become higher than the applied load, then it will not break. But when applied load become higher than internal resistance of the material, then it will break down. Okay. Now, I like to see that it has a multiple force working in this stone, but I like to cut it right over here. I like to check that how many force will work there. So I cut it into this like a potato. You just slice with a knife, right? So we know there will be one force should work perpendicular this surface. So if I cut it, this is x-axis, this is y, and this is z-axis. This is y-axis, this is x-axis. Then along x-axis, there will be one normal stress. So that normal stress, I can call it sigma. And since it is working along x-axis, I call it sigma x. Now, I give you an example that if you cut a body in that surface, there is two force work. One normal stress, other one shear stress. So shear stress, we don't know actually the direction, but we know there is a shear stress. So we are thinking shear stress work parallel to the surface along this direction. Now, if I know this angle, this shear stress, I can divide into two components. That one shear force working along this direction, other one shear force working along this direction. So what you see? If you cut a object, then perpendicular to the surface, there will be one normal stress. That means sigma x. And what is the other two axes? Other two axes remain y and z. So other two directions, there will be shear stress. So right over here is showing this is sigma and this is tau. And this tau, then they divide into two parts. One part working along this direction, other part working along this direction. That is showing over here. This is sigma x, and this tau working z axis, they are saying xz, and upward direction working tau xy. Okay. So the normal stress we express with sigma. If it is tension, then normally call it positive sigma. If it is compressive, then we call it negative. And tau, they have some sign of the tau, we'll talk about later on, but tau always work parallel to the surface. So this body, what you see, how do I cut it? I cut it vertically with a knife. So along this axis, if I say this is x-axis, along this direction is y, along this direction is z. So I cut a knife on YZ plane, I cut it, right? So this is YZ plane. This is Z, along this Z, this is Y. I cut a knife. So this perpendicular to this surface going along x-axis. So this sigma I will call x, and I have tau. That tau, one working y direction, other are working z direction. So I know there is two tau, one tau, other tau. Now the sigma working along x-axis. So all of them I put first x. Now this tau working along z-axis, I'll call it tau xz. And this tau working upward, so I along y direction, so I'll call it tau xy. Similarly, if you cut this body along this direction, then what will be the sigma? You see, sigma will be along this direction, right? Up and up to the surface. Then sigma will be, the normal stress will be sigma y. Now, how will be the tau? You just put two tau, one tau, comma, other tau. Now, both tau, you put y. That means this tau coming related to this sigma y. Then y-axis, what is the other two axes? X and z. So one will be tau yx, other will be tau yz. So right now, just remember that if you cut a body, in that surface, there will be one normal stress and one shear stress, but that shear stress, we can divide into two shear stress. Okay. So remember, there will be one normal stress and two shear stress if you cut a point in a certain plane. So we can, yeah. Any questions? Any question? Anyone?